So think about the last time you set up a fresh Ubuntu instance, and it could be your primary developer workstation, a specialized WSL environment, or a Pi hole on a Raspberry Pi filtering your home network. You spend hours, maybe days, installing software, tweaking configurations, getting it exactly how you want it. But what happens when the hardware fails or it's time for an upgrade? So you're forced to repeat the entire click and type tax from memory. So in the enterprise world, there is a metric for this, RTO, or recovery time objective. And it's the maximum allowable downtime before a failure severely impacts operations. And for a business, downtime costs money. And for you as a developer or a hobbyist, downtime costs sanity and productivity. So whether it's your corporate workstation or your home DNS server, your desired RTO isn't days, it's minutes. So you want to get to your exact desired state as quickly as you possibly can. So this is why we use YAML. YAML is a human-readable configuration file. It's lightweight and dead simple to version control and validate against a schema. You describe the exact end state that you want, and the engine ensures it looks that way every single time without side effects. With YAML, you're not performing privilege escalation and then using these privileges for command injection with disregard for error handling. And the Cloud Init daemon already runs with the necessary system permissions at first boot, and it securely executes the declarative state that you requested. It's all done through a locked down, pre-written system of APIs. But we aren't just using YAML to configure Ubuntu. We're using it to configure the entire software stack that's running on top of it. So if our goal is a near zero RTO and our format of choice is a simple YAML file, how does the machine actually read that file and build itself? So across the Ubuntu ecosystem, it happens through a combination of three distinct stackable YAML layers, and they form the ultimate developer workspace. So let's look at this three-layer cake. Layer one is auto install. This is the foundation. It handles the birth of the base operating system, partitioning disks, configuring full disk encryption, and installing the Ubuntu OS. Layer two is Cloud Init. Now, this is the framing. It handles the initial boot configuration, creating users, installing packages, setting up network routes. And layer three is Workshop, the interior design. So this is the project-specific configuration that builds the isolated developer sandbox without disrupting the host OS. Now, auto install handles the bare metal resource configuration. It answers where is the disk, how is it partitioned, what is the host name, and it gets Ubuntu onto the drive. Now, instead of a human sitting there clicking next, next, next on a keyboard, choosing time zone settings, auto install reads a YAML file, and it completely automates the traditional OS installation phase. It will configure your full disk encryption and even enroll the machine to Canonical's centralized management solution, Landscape, where a remote backup of the disk encryption recovery key can be stored. Now, Cloud Init is a Canonical-led project since 2007, with active participation from both our competitors and our partners. It is the industry-standard multi-distribution package that handles early initialization of an Ubuntu instance. Now, Cloud Init looks for a cloud config YAML file, and when it finds it, it executes a series of instructions in a strict, predictable order to configure your OS user space quickly and reliably. And maintaining an updated Cloud Init file for your servers and workstations ensures your RTO is short. Now, layer three is workshop.yaml. It is the project-level configuration file. And while auto install and Cloud Init build a secure, isolated house, Workshop configures actual tools inside the room. Now, software developers don't just work on one thing. They juggle multiple projects over time. So project A might need Python 3.11, Postgres, and a specific AI agent framework. and project B might require Node.js 22 and Redis. And now workshops allow you to work on both projects with zero host contamination. So instead of installing all these competing dependencies directly onto their host OS and creating a cluttered mess, developers maintain a distinct workshop.yaml inside each project's Git repository. And Workshop reads that specific YAML, constructs a dedicated container sandbox, and drops the tools inside and gives you a pristine environment tailored only for that project. Now, the beauty of this stack is that the YAML you write to configure a local AI sandbox in a container is functionally identical to the YAML you use to deploy a server in a data center, in a virtualized environment, or on a cloud. It is the exact same skill set. This brings us to the next question: where do we actually use these YAML files? And the answer is a massive continuum that stretches from global data centers all the way down to a tiny edge device like a Raspberry Pi. And what makes this technology brilliant is that you're using the exact same configuration language across this entire spectrum. So we start at the macro level, the public cloud. Now, this is where Cloud Init was born. If you spin up an Ubuntu VM on AWS, Azure, Google Cloud, Oracle, IBM, or elsewhere, Cloud Init is already baked into that image and is the invisible force that configures millions of cloud VMs at scale every single day at their very first boot. Now, here is a simple, practical example of that cloud scale utility. This is a lightweight Cloud Init file that performs the bare minimum required to deploy a strictly confined Pi-hole snap package on Ubuntu LTS or Ubuntu Core. And with a single file, it writes configurations to disk, it installs the snap packages, and reliably handles starting and restarting the underlying services. So from a security hygiene perspective, this is better than curling a script and piping it to sudo bash. Now, moving inward from the public cloud, we land in the enterprise data center. When provisioning bare metal servers on racks in a data center environment, MAS, Metal as a Service, is the correct tool to reach for. MAS configures your hardware stack and can be used to deploy Linux or hypervisor software like VMware ESXi. And MAS has an instance metadata service, or IMDS for short, that feeds Cloud Init with information on first boot. Now, Cloud Init support is natively available in every major virtualization platform. For example, VMware Cloud Foundation, or VCF for short, also runs an instance metadata service. Now, Ubuntu instances launched in VMware natively consume centralized information about availability zones, geography, and other environment metadata from VCF. So if you're not using MAS to manage your racks, you can pair auto install with Cloud Init to provision machines. And both MAS and auto install leverage Curtain under the hood to handle low-level storage and disk partitioning layouts, and to write the base OS to the hard drive. Now let's bring this home to something we deal with every single day, our local workstations. We can use that exact same enterprise cloud scale engineering and run it right on our laptops to manage our daily developer environments. So for Ubuntu desktop users, the auto install YAML file is consumed by the Ubuntu installer, and it can be downloaded from the web or uploaded locally during Ubuntu's installation. For corporate Ubuntu desktop users, an auto install YAML file can be served to workstations across enterprise environments through Landscape. And employees must know the domain name where Landscape is running, authenticate via SSO, and the Ubuntu installer self-provisions using the auto-install YAML file downloaded from Landscape. For Windows users, we can instantly spin up standardized, reproducible virtual environments using WSL, and instead of spending days manually tweaking a local environment for a new project or onboarding a new developer, you simply launch the WSL instance via YAML. So Landscape allows you to instantly provision a WSL instance running Workshop. WSL even provides native access to the GPU, so you can easily apt install CUDA or apt install Rockham that can be part of your Cloud Init configuration. And this allows open source models to leverage your GPU for maximum performance. And we go a layer deeper, straight into isolated containers. Now remember that workshop.yaml file that we discussed earlier, it lives within your project's root directory. So when you git check out your project's code on Ubuntu desktop or your Ubuntu WSL instance, Workshop spins up LXD system containers to build highly isolated project sandboxes. So why does this matter? Consider the rise of agentic AI. If you're using autonomous AI agents to write and test code, you likely don't want all of them running wild on your host machine. So by defining a project-specific workshop.yaml, Cloud Init configures a LXD system container that acts as a secure confinement layer. The AI agent gets a pristine playground tailored exactly for that project, and your host machine remains completely uncompromised. Finally, we land at the micro level of our continuum, the IoT edge, and this means Raspberry Pis, smart factory gateways, and remote network appliances. So in this ecosystem, the Snapcraft YAML file contains instructions to package software as a snap. And the gadget YAML defines the target hardware and boot process. Model assertions cryptographically declare exactly which components belong on the device, and we use a tool called Ubuntu Image to compile these three elements into a flashable Ubuntu Core image. Now, these steps are relevant when you have your own hardware, but it's easier if you're launching Ubuntu Core on public cloud, because then Cloud Init is the only YAML file that you need to use. Multipass, LXD, and Workshop are essential components if you ever plan to build your own strictly confined snap. So be sure to include these packages in the auto-install YAML file that you compose for your own Ubuntu desktop. And let this day mark the end of your use of curl pipe sudo bash to install software forever. So the modern answer is packaging applications as strictly confined snaps, and lean into AI delegation. Have an AI agent inside your workstation build those snaps for you, and use Cloud Init to stage and test the installation path of your confined snaps on an Ubuntu Core instance, virtualized in Multipass. So let's look at how this elegant confinement works in practice on a Windows machine utilizing WSL. So on the screen, we are currently inside a project directory using PowerShell. And then by entering the WSL command, we seamlessly drop into our Ubuntu environment. And then from the Ubuntu CLI, we can launch VS Code installed on the Windows host machine by typing code space dot. And I'll wait for this to wrap up. There's my workshop YAML file. I've got my terminal in VS Code. Okay, so looks like I've jumped ahead here. I'm launching workshop launch, and this creates the new dev workshop in accordance to what's in the workshop.yaml file. And once that gets kickstarted, workshop is running inside a confined container within WSL, and I'm able to run my cloud agent once it gets installed here. Yep, dev has launched. So note that there is a WSL indicator on the bottom left, and that appears when you've got a secure connection between VS Code on the Windows host machine and the WSL instance. I've already run the workshop launch command. So now we've got this sandbox with cloud running inside of it, and we're protected. The host machine is protected from nefarious prompt injection attempts that could originate from an unverified code base. Yeah, so we're here going to validate my Snapcraft YAML file, and looks like I've run out of credits, but once you've accepted the operational risks of allowing cloud to access your local code directory and connect the CLI with your Anthropic developer account, it's off to the races. So I'm happy to take questions if there's time.